Hey, honestly, it feels like we've pulled something straight out of science fiction. We're talking about a flesh computer.
Yeah.
Seriously, a commercial hybrid of silicon chips and actual human brain cells that you can rent.
Yeah, it's pretty wild. And the source for this is an article that just dropped in Science Alert, July 3rd, 2025. It's titled, "You Can Now Rent a Flesh Computer Grown in a British Lab." So for this deep dive, we really want to dig into what this actually means,
Yeah.
get past the headline shock.
Exactly. What are these things, really? Why now? Why is it such a big leap? And yeah, what does it mean for things like, I don't know, energy use, understanding our own brains, the whole lot? Get ready for some real whoa moments, I think. Okay, let's just take a breath. Flesh computer, it's quite a term. So the CL1 computer, what is it fundamentally? Like, how is it built?
Right. So at its heart, the CL1, it's got about 800,000 neurons, human brain cells, and they're grown like directly onto a silicon chip. It's not just cells in a dish, though. It's got a whole life support system built around it,
Hmm.
keeping them going. And the big thing is, it's the first time this kind of silicon brain cell hybrid is actually being offered commercially. You'll be able to rent access to it.
Wow. Okay. That's a big step. How did we even get here? Where did this idea start?
Well, it really kicked off with an Australian biotech startup, Cortical Labs. They've now partnered up with a UK company, Bit.bio, to sort of scale things up. But this builds on something they did back in early 2022, I think, called DishBrain. You might remember that. It was the system that learned to play Pong.
Oh, yeah. I remember Dishbrain. That made
Exactly.
waves.
That was kind of the proof of concept. They were exploring this whole idea of wetware, which is
Yeah.
basically, computing using actual living biological stuff, neurons in this case.
Okay, so wetware. Got it. So if I'm, say, a researcher, how do I actually use this thing? Do I plug in a keyboard or...
Huh, not quite a keyboard. It's actually pretty clever. Users can send specific patterns of electrical stimulation, basically code, directly into the neuron system. The cells are sort of trained, or they learn, to interpret these signals as inputs, as information, and they respond like almost instantly. You can read those responses. And interestingly, these neurons, they're grown from skin and blood samples given by adult human donors.
Right. Okay, so you're essentially programming living tissue with electricity. Now, this is where I get really curious. Why do this? I mean, we have incredibly powerful silicon chips already. What's the big advantage here?
Okay, yeah, this is crucial. The number one advantage, the one the article calls very significant, is energy. Think about it. The CL1, okay, it's not going to beat a supercomputer in a drag race, not yet anyway, but the energy it uses, it's tiny.
Yeah.
A minuscule fraction. We hear constantly about AI centers needing like countries worth of energy.
Well, yeah, the consumption is insane.
Right. But a whole rack of these CL1 machines, it might only use about 1,000 watts. That's just a completely different scale. It changes where you could potentially use this kind of intelligence. Think edge computing, places with limited power.
The energy angle is huge,
Yeah.
definitely. But is there more to it than just efficiency? Does the biology itself bring something different to the table, something silicon struggles with?
Absolutely.
Yeah.
That's the other key part, is the inherent ability of neurons to, well, learn and adapt in real time. Cortical Labs themselves put it really well. They said something like, the neuron is self-programming, infinitely flexible, and the result of 4 billion years of evolution.
Hmm.
What digital AI models spend tremendous resources trying to emulate, we begin with.
Hmm.
And that's not just, marketing fluff. It points to how brains handle messy, real-world information, learn patterns and noise, things that digital AI often needs massive, clean data sets and tons of training for.
So it's like built-in learning capability honed by evolution. Have they actually tested this? Like put the wetware up against standard AI?
They have, yeah. Brett Kagan, a neuroscientist involved, and his team did exactly that. They basically set up tasks where their cell cultures competed against equivalent machine learning algorithms.
Hmm.
And the results, pretty striking. The cell cultures actually performed better on those specific tasks.
Wow. Outperformed them.
Yeah. It really suggests there's something fundamentally different, maybe more efficient in some ways, about how biology processes information.
Okay, so let's connect these pieces. We've got energy efficiency, this innate learning ability. What does it all mean in practice? What are the big potential uses for these rentable flesh computers?
Well, probably the biggest immediate potential is as a research tool, like an unprecedented one. It gives scientists a whole new way to study our own brains, right? How they work, how they learn, maybe even things like creativity. It could blow open doors in neuroscience, cognitive science.
Can you give a concrete example, something that really shows its power for research?
Sure. Brett Kagan mentioned one that really stuck with me. He said something like, Epileptic cells, so cells cultured with characteristics of epilepsy, they can't learn to play games very well. Makes sense. But, he said, if you apply anti-epileptic drugs to that culture, suddenly they can learn better. Plus, you can measure all sorts of other things you couldn't access before.
Ah, okay. So drug testing, essentially. But on a functioning, learning neural system.
Exactly. Ethical drug testing. You can see how compounds affect complex brain functions, learning, activity patterns in a living system without needing human trials right at the start.
That's huge. That
Yeah.
is genuinely impactful. Okay, but there have to be downsides, right? Limitations. It sounds almost too good to be true.
Yeah, fair point. There are definitely practical hurdles right now. For instance, the neurons they're using currently only survive for about 6 months.
Ah, okay, so they're not permanent fixtures.
Not yet, no. You need to replace or regenerate them.
Hmm.
And then there's the commercial side. The first units, these CL1s, they're apparently going to cost around US $35,000 each to buy.
Oof, steep.
Yeah, it's specialized gear. Or you can rent remote access, which is maybe more accessible, for about $300 a week. So it's cutting edge, powerful, but definitely not something replacing your laptop anytime soon. It's a high-end research tool for now.
Right. So, summing this up then, we've dived into the CL1, this flesh computer, an amazing blend of human brain cells and silicon. We've seen the incredible energy savings, how it taps into biology's natural knack for learning, something digital systems are still trying hard to copy, and that potential as a tool, especially for brain research and drug discovery, seems really profound.
It really is a potential game changer. It's not just about a new, maybe greener way to compute. It's also this unique window we're getting into how intelligence, biological intelligence, actually works. It forces us to think about, what other kinds of intelligence might be possible, how biology computes so efficiently.
Exactly. And it leaves you wondering, right, if we can now harness this self-programming, infinitely flexible power that took billions of years to evolve, what does that unlock? What new kinds of understanding, what new forms of intelligence might emerge? And how does that change what we even mean by thinking? Definitely something to mull over. Stay curious, everyone. Hey, honestly, it feels like we've pulled something straight out of science fiction. We're talking about a flesh computer.
Yeah.
Seriously, a commercial hybrid of silicon chips and actual